Okay, sorry for the wait. So today is our second GP seminar of this semester, and we are very happy to have Jean Suemnicht. So Jean Suemnicht is a registered professional geologist with more than 45 years of professional experience in geothermal exploration and development throughout North, South, Central America, the Caribbean, Europe, and the Middle East, Africa, and Asia. His background includes extensive work in geology, geochemistry, geophysics, and geothermics. He has been the principal investigator for DOE-funded research and technology development programs in wellbore geophysics and enhanced geothermal systems. He worked for Unocal Geothermal for 17 years and was exploration and development manager for ORMAT Technologies until becoming an apprentice Incorporated, where he has been responsible for geothermal resources evaluation worldwide. Jean served on the governing board of Geothermal Resources Council and the Geysers Geothermal Association, and is a member of International Geothermal Association, American Geophysical Union, and the Geologic Society of America. He received the Joseph Aidlin Award from the GRC in 2015 for his leadership. So with that, we'll let Jim give us the talk from Geothermal 101. So online audience, could you please mute yourself?
Or you'll keep scaring me. I'm not sure which.
I think you can find who is making that noise and then you can
So we have a pointer. Or
Yes.
I suppose I can activate. I don't see where I can activate the laser pointer here. Thanks. I'd like to keep this interactive, if at all possible. If there are questions, please feel free to interrupt. Okay. So I appreciate the opportunity. So this is intended to be just a basic discussion of exploration and development for geothermal resources. I'd like to stick strictly with that. I try to steer away from politics and finance and everything else that goes into developing a geothermal resource, but in this particular case, just focusing on geosciences behind exploration and development. So the question becomes, what exactly are we exploring for? And why won't my computer work? Geothermal exploration is at its base the search for heat. Everything else that we search for is actually the effect of heat. And that seems like a relatively straightforward proposition because the Earth is an active planet and it's always losing heat from the interior. We deal with and explore the very, very thin crust of the planet. So on this globe, what we access is really the upper 10 or so kilometers of crust, which is on this globe is about the thickness of the paint. So that's what's accessible now. But the problem with exploring for heat is that it's not evenly distributed. Whoops. So, for example, take in this particular example, the Basin Range. So here in the Sierra Nevada, the heat flow is relatively low. The increase as you go deeper is a lower gradient than out here in the Basin Range, where the temperatures increases much more quickly. So everything to the west of the Rocky Mountains is highly prospective because that's the tectonically active part of the crust. In the Western US, we have either a consuming continental margin, which gives us magmatic heat into the crust, or a very, very thin crust across the basement range, which raises the asthenosphere and gives us access to deeper heat. And that's why worldwide over the last several decades, geothermal exploration has been concentrated on the tectonically active areas of the world. So what are the basic elements of a geothermal system? Well, first we need a heat source, a relatively young heat source. What's relatively young? Well, we're all geologists. 5 million years ago was relatively recent. But let's say within the last million or so years, a preferential magmatic heat source if we can, but out in the basement range, you could also have very, very thin asthenosphere, or very, very thin crust and very, very shallow asthenosphere. So you would wind up getting higher temperatures at shallower depths. We also need a source, fluid, circulating hot water through permeability, the holy grail in geothermal systems. Because you can have heat, you can have fluid, but without circulating that fluid through fractured rock, you can't really mine heat efficiently out of the rock. So most geothermal systems are classed on the basis of their heat content, their enthalpy. So very much higher heat content allows you to take a fraction of steam or native steam in the crust and use that to pipe to a geothermal turbine and generate electricity. That doesn't necessarily mean that the rest of the resource isn't useful. We can use very much lower temperature resources for direct use. That's been going on for thousands of years in baths, in heating houses, space heating, things like that. We can also use relatively intermediate temperature sources to generate electricity, but with different technologies. So most everything that we'll talk about today is just conventional geothermal systems. This set of hydrothermal systems where we can actually source that fluid circulating in the crust, bring it to the surface, and pipe it to turbines so we can generate electricity. Again, we can have a discussion about all the other sources if you want to, the questions anytime, but usually conventional geothermal systems are classed on the basis of exactly what you're doing with the fluid. So higher enthalpy resources, say for instance, like a dry steam system, like the geysers in Northern California, the largest developed geothermal system in the world. You can take steam directly from the ground, pipe it through a turbine, spin the turbine and generate electricity. Or in higher enthalpy systems, you can flash a small fraction off of that fluid that you're producing to the surface and use that to spin a turbine. That's a very common technology in the Imperial Valley, which is east of here, that stretch of desert between here and Yuma. Or in lower enthalpy systems, things like around 175 to 150 degrees C, you can use a secondary working fluid to exchange heat between the geothermal fluids and low flash fraction refrigerant or something like isopentane, isobutane, and use that to spin a turbine. Yes.
Could you explain the flash tank? The flash tank, is that hot water, the pressure drops and turns the steam into tank? Is that?
Yes. And so you take part of the steam fraction off and re-inject the fluid. And thermodynamically, you only get a certain percentage of the steam from any given temperature. Any other questions? Yes.
So we've been talking about fluid. It's like usually water. Or
Yes.
Okay.
Although maybe later on we can talk about other fluids if you have
Okay.
questions about that. Sure. Yeah, there are other things, but sure. But that's the unique thing about binary systems here is that you're not necessarily using the water except to mine the heat out of it. You're not using it directly.
Gotcha.
So you're putting all of it back in the tank.
Gotcha.
Okay. So this is a diagram that everybody loves to hate. I did it this way because I wanted you to be able to read it, but everybody's exploration timeline is very much more complicated than this. there are all kinds of things that, like I said, we don't want to talk about all the permitting and compliance and financing and power plant building and all the rest of that stuff. But for this particular case, just a very simple timeline. Basic exploration takes about 5 years to get to an actual developed system where you're at this particular stage. And it starts way back here with basic geology, geophysics, and geochemistry. And it increases in cost. Geologists are relatively cheap. But as we get deeper and deeper into different methods, the price goes up exponentially. So let's look at this in terms of different exploration phases. Let's look at the first year. So now we're paying attention to basic geology. And we're looking specifically at the right geologic, hopefully the right geologic setting in the right place, the right time. And it's very fundamental. So indulge me a bit. I'm a geologist. For me, it's all about the rocks. So we're looking for heat. And one of the most easily accessible examples of heat are volcanoes. Now, volcanoes are not always erupting all the time. They're not always putting out heat all the time, or they are always putting out heat all the time. But a lot of the things about the detailed stratigraphy, the structure, age relationships, location, and surface manifestation, all those things are very, very important clues about where a geothermal system might actually exist. It all starts with understanding the rocks. So let's take an example. How many of you recall the eruption of Mount St. Helens? The two people who were alive at that time. Okay. I always run into this problem because I asked that question and most of the people weren't even born then. But anyway, the eruption and the collapse of a Cascade volcano just a little bit north of Portland, Oregon, back in the 1980s. Okay, very spectacular event. But that event only produced about a single cubic kilometer of new magma. That's impressive. Certainly disrupted things in the Pacific Northwest for a considerable period of time. But on this sort of volcanic explosivity index, think of this as kind of like the Richter scale of volcanoes that the USGS came up with. The eruption of Mount St. Helens here is comparatively small to the very much larger scale eruptions. So another comparison would be something like Long Valley Caldera here, that some of you may be familiar with if you ski. This is Mammoth Mountain right here. This is Mona Lake and Lake Crowley. This is all Eastern Sierras. So in comparison, the two systems. Well, Mount St. Helens erupted only a single cubic kilometer of magma. Long Valley erupted 600 cubic kilometers of magma, producing the Bishop Tuff, a massive ash flow sheet that blanketed the whole arc. Now, generations of suffering petrologists have established that that only represents about 10% of the magma that's in a magma chamber supplying that eruption. That means it's a tremendous, huge resource that gives you some focus on the idea of that's a tremendous heat engine in the crust. That's really a geothermal prospect. So, technical difficulties. Hot springs are also a very important resource because they can give us lots of ideas about where fluid is coming from, where it's going to, and what's happening within a circulating geothermal system, which is why we spend so much time and so much effort in collecting samples of all the surface manifestations. Yes.
Julie just got one script, it plugs in and blocking the screen.
Wouldn't it be easier with just a poster?
I think think usually if you just like close out of the settings, it automatically closes that. Or yeah, if you just want to drag it down. Oh, nice.
That's okay.
A quick review. One more, or maybe two more. Yeah, two more. Yeah. So we spent a lot of time, a lot of effort collecting samples from gas, fluid, all the things that come to the surface. So an illustration. Geothermal fluids can be briny. In this particular case, I've chosen some that aren't particularly briny. But a sample worldwide from Iceland all the way to locally here in the Basin Range or in California. So this is Casa Diablo in Long Valley Caldera. Iraqi is in New Zealand. All of this is either a Yellowstone or Old Faithful Geyser in Yellowstone, and Geyser in Iceland. No, that's not a typo. It's their word, and that's how they spell it. So most geothermal brines are not as briny as seawater. Now, that's not to say you can't have very high concentrations in geothermal brines, but for the ones I've chosen for this illustration, not as briny as seawater. But if we take a look at things like silica, there's a marked difference. Why?
Continental crust is high in silica.
It is. Why? What's the difference? Seawater is much, much higher in fluoride, but geothermal waters are much, much higher in silica. It's hotter. Hot. Exactly. It's heat. And that's the core of almost all hydrothermal chemistry. All of the things that we talk about, dissolved solids, trace elements, isotopes, gases, are directly related to the heat in the geothermal system. And something like silica increases in concentration almost monotonically over the constant temperature increase in geothermal systems. So the silica content of the system at 150 degrees C is completely different than the silica content of the system at 200 degrees C. And that allows you to calculate exactly what the source temperature of the fluid might be. And with changes in silica phases and changes in circulation, it'll also tell you something about where the fluid has been and what's been happening to it on the way to get to the surface. So geochemistry is an extremely important element in geothermal exploration. So we've come to this part of the timeline. We're at a decision point. We know as much as we can about the basic geologic background. We're continuing to build a geologic conceptual model in our head. We've got constraints from geochemistry and geology, but we still don't have any constraints about the third dimension. We don't know all that much about what's below our feet, except what we can extrapolate from geologic maps. So that's where geophysics comes in. Geophysics allows us to start to constrain the third dimension. And it also gives us an idea of exactly some of the distribution and shape of the system. Because all of those things that are related to heat, all the alteration, the change in minerals, are changing the physical characteristics of the rocks. They change the conductivity, they change the magnetic susceptibility, they change the density. All of those things can be measured in geophysics. So one of the very, very relevant tools is MT, magnetotellurics. The Earth is a magnet circulating in, or rotating in a magnetic field, an electrical field, sorry, the solar wind, and that generates earth currents, telluric currents that can be measured if we wind up setting up a system to measure both the electrical field and the magnetic field of the Earth. It's a very less intrusive method than many galvanic resistivity methods. And resistivity is very, very important because all of those alteration changes in the geothermal system have essentially generated clays that are conductive. And we can measure the resistivity of the rocks. Those resistivity changes, if they're related to heat, are related to a geothermal system. So this is an illustration of at least one interpretation of a geothermal prospect. Magnetotelluric interpretation has improved markedly over the years. So from a 1D to 2D interpretation and 3D interpretation, it gives you a much clearer picture of exactly what the resistivity structure is in the earth. So like most ore forming systems, as you go deeper, you get away from a lithocap or a cap rock to an ore forming system or a geothermal system. That cap rock is usually clay rich, very conductive clays. But as you can see in these three cross sections at different depths, as you get into the geothermal reservoir, the resistivity changes again. It's not necessarily low. Why? Because at higher temperatures, the alteration minerals are different. You've changed to more orderly silicates. They're not as conductive, and therefore the resistivity picture changes. But one of the important things to note in this is in this upper interpretation, you notice the very close relationship to temperatures. These are measured temperatures in the wells that run this cross section. So just like fluid circulation, the resistivity related to the alteration in this system very closely follows the cap rock to the system and eventually the geothermal reservoir. Questions? Okay. So we've completed the semi-inexpensive parts of our timeline. We've completed a decent geophysical survey. We think we know a pretty good conceptual model of the geothermal system we're searching for. But we still don't know anything about that fundamental element, heat. And the only way to do that is to drill. It's the only way to prove heat exists in the system. Geophysics can be used to identify things like copper deposits, gold deposits, any number of mineral deposits in the crust, but they can be related to everything way back into the Paleozoic and not necessarily to current heat. So the only way to do that is to drill. And most of what we're measuring is conductive heat flow. And you do this experiment every single time you cook. So the pot, in this particular case, is conducting heat to whatever is contained in the pot. And the convecting fluid in the pot moves that heat so efficiently that it keeps the pot from melting. So convection in a geothermal system is an extremely efficient way of moving heat. And that's why we're looking for exactly those conditions, because any geothermal system is a major thermal disturbance on the crust. And the convection within that system makes it look completely different than the background conductive heat flow. So the basic principle of conductive heat transfer, the change in temperature with depth in the earth relative to the conductivity of the material. And most rocks are very low conductors. We can exist on the surface of the earth just because the rocks are very efficient insulators. So conductive heat flow in the rocks is very poor. And that's why the contrast with a convecting geothermal system is so important. So we're looking at all of the things that can affect the heat flow, just like any geophysical signature. There are all kinds of corrections that have to be made in order to understand gravity or understand magnetics. Same thing applies to heat flow. There are all kinds of surface effects. There are all kinds of subsurface effects. And the unfortunate thing about subsurface effects is if you look at that list, a lot of the things that we're actually looking for in the subsurface in a geothermal system are things that interfere with the heat flow picture. And what we're really looking for is that convective transfer that's such a sharp contrast with conductive heat transfer. So most times in geothermal exploration, things are plotted on a temperature depth plot like this. We're looking at the change in temperature as we go deeper, just like that early map that I showed in the United States with the Western US. We're looking for rapid temperature changes. And instead of red to blue, these are the numbers that are related to that increase in conductive heat flow, linear conductive heat flow. But since we're dealing with circulating fluid in the crust, we're dealing with the boiling point of water with depth. So as we go deeper, pressures get higher, boiling point of water increases. You can think of this sort of like the speed limit. Almost the core of every convecting geothermal system conforms to the boiling point depth curve for water. And everything on this side of the curve is steam, everything on this side of the curve is fluid. And this line represents the maximum enthalpy of water before you make that phase change. So imagine for a moment that you're the investors in a renewable energy company. You have a geologist who's come to you and said, I have this fantastic prospect area. You wouldn't believe this place. It's so great. You don't invest your money. You're going to drill some temperature gradient holes. Some shallow ones, the ones that are easy to permit with the federal government or whoever the agency is that you're working with, and relatively inexpensive, say, I don't know, 150 meters. That's an important depth because at 150 meters, somewhere up in here, you have to be out here on the boiling point depth curve at 150 degrees C. That's the reason that most of the permitting agencies in the United States and sometimes around the world say, wait a minute, 150 meters is about the limit, because you can get into a lot of trouble very fast without blowout prevention equipment on well. So, geologists are so convincing. You're going to invest your money, right? Because you want to buy a new yacht. You want to develop a geothermal system. You want to become, well, an energy entrepreneur. So we agree to rig up, drill a pattern of 150 meter temperature gradient holes. They're the results. What? Wait a minute, you told me we were supposed to be over here. What happened? Is this encouraging? Show of hands. How many would drill deeper? Just water circulation? Yes. No brave souls? No, come on. The geologist is so convincing. It's such a lucid discussion of the conceptual model of this area. All right, we'll give you some more money. We'll allow you to drill temperature gradient hole to 300 meters. That's pretty typical. Yes.
So this looks like this, in that case, that it's lower than the standard geothermal gradient must be because of convection is active there.
Hasn't even affected it. That's conductive heat flow. And darn low, too. It's hard to grab for your wallet and give the guy more money, right? But so convincing. It's all right. We'll let you drill some 300 meter holes. That's all right. I hate to do this, but all right, I'll give you the money. 300 meters. Whoa. It's a little more encouraging. Looks a little better. Show of hands. How many would drill deeper? One brave soul. 2, 3 brave souls. All right, put your money on the table. Now we're going to drill to 600 meters. We're going to find out a little bit more about whether this guy has his conceptual model in one piece. So we rig up, we drill to 600 meters. What? We're still not over here where we're supposed to be. What's going on here? Something wrong with the conceptual model? But geologist is so convincing. has a great model in mind, keeps selling you on the idea. How many of you would drill deeper? Jeez, I can't convince you? Well, at least one money pockets, Mr. Moneybags here decides, all right, I'll give you some money. We'll drill to 1,000. Find out exactly what's going on. That's exactly what we do. What do we find? And this is not a hypothetical. Makes you happy, but it's actually a series of gradient holes that were drilled in Newberry Caldera. You may be familiar with Newberry. It's a eastern Oregon volcano, about 4 by 5 kilometer collapsed caldera. Has 3 caldera events, 78,000 and about 50,000 years ago. So this series of obsidian flows right here erupted 7,000 years ago. These erupted about 3,500 years ago. This erupted in 660 AD. A wide, large volcanic system in the crust has a series of eruptive events that covers about 2,000 square kilometers. Very viable heat source. And those temperature gradient holes, as you can see from the small map, were drilled right over here. So this flow. The fundamental lesson, understanding the geology is extremely important. Why can't we do something that's viable, that's actually useful within the upper 500 meters of that hole? Well, what are calderas filled with? A lot of loose pyroclastic material, some broken up flows. What about the hydrology? Well, everything is flowing across the caldera from high to low. So a lot of the hydrology is going to interrupt whatever's coming from down below. What does the resistivity pattern show you? Down to about 300 meters or so, relatively high resistivity, just because of course it's all unconsolidated material in the interior of the caldera. And until you get into bedrock, you're never really going to sense the true conductive heat flow, because all of those things that are interrupting conductive heat flow are affecting the signal.
Is that because those material is very poor heat conductors?
Yes, that, and also very full of water at depth. So that one bump in the 300 meter section, that's hydrologic interference from the cold water aquifer. So all of those things, just like any geophysics, like, require some geologic background to be able to interpret. So it takes that understanding of the geology to continue to explore to depth. Questions? Yes.
In this example, did they have geophysical surveys?
Yes.
And like, did the geophysics also indicate that there was a heat source further at depth?
The only thing that indicates a heat source is, well, you're talking gravity interpretations, things like that. Yes, that's an inference because you're still looking at inferring. But the main inference is the geology itself. Again, 680. Yeah. Big obsidian flows, spectacular. If you ever get there, it's fantastic.
So basically that cold layer on top of bedrock is filled with cold water circulating only in the, in top layer.
Either that or no water and just poorly conductive material. Because remember, it's change in temperature with depth and also the conductivity of the material. Things like clay, pumice, loose rocks are very poorly conductive. Very poor. So the conductive heat flow is not going to come. Other questions? Yes.
So like during the drilling, we also take off the material and examine that?
Yep. Yep. So all of the constraints on saying loose material and pumice and so forth at 300 meters, that's all part of, that helps you constrain the rest of the geophysics. I know that to some people, geophysics is its own But it's all constrained by the geology. Sorry.
Yeah, like, how many holes do we need to drill at once?
Well, they drilled 2 here. Usually, a lot of times, exploration companies will get into pattern drilling. So in something like the Basin and Range, where one-dimensional heat flow actually works, you can drill a pattern. That was a very common exploration tool. Other questions? Okay, so in geothermal exploration, you want to get to this particular picture as quickly and cheaply as possible. This is the goal, because understanding the heat flow within the system, specifically related to convection, is key to the core of the system, discovering the core of the system. The heat flow around a convecting geothermal system very closely follows fluid circulation. It's an important clue in getting into the system itself. So in our exploration timeline, we're finally at a decision point, a crossroads. Every geothermal system depends on having a full-scale well to determine the productivity of the system. You have to rig up and drill a full-size well. And if you're successful geothermal well has a huge volume of fluid that you can produce to the surface. But exactly how much is large? Well, if you had a water well that produced 200 gallons a minute, there was a very nice supply of fresh water. If you had an oil well that produced 200 gallons a minute, if you had an oil well that produced 200 gallons a minute, we wouldn't be having this conversation. That translates to 6,857 barrels a day. I checked the price of oil this morning, depending on where it comes from, how nice it, how clean it is. It's varying between $75 and $79 a barrel. That translates to $511,000 a day, or just a few tens of millions shy of 200 million a year. But in a geothermal system, in order to be commercially successful, you've got to produce 2,000 gallons a minute. Very high volumes. So for comparison, you've drilled your successful well. There you are. What have you got? Nothing really, because it takes at least 3 wells to prove that you have a sufficient reservoir volume and that you can test and show that you have a system that will sustain production for a 30-year span of time, so you can recover investment on your exploration program. So that example, the well of 2,000 gallons a minute, that one well would be capable of producing about 5 to say 7 megawatts worth of electricity. How much is a megawatt? In a developed society, the general electricity usage is a megawatt per person. So you're looking at enough electricity for 1,000 people. And if you want to have a 50 megawatt generating plant, very common size within many geothermal developments, you're looking at somewhere between 5 to 7 wells. And that's not including injection wells, makeup wells, a few dry holes, and all the other things that go along with it. And after all this period of time, you still don't have a plant at the surface. You haven't put in the piping. You haven't connected the transmission lines. You're still 2 to 3 years out from having any money coming into your pocket. Everything in exploration is the basis of trying to establish the fundamentals of a developed geothermal system so that you can get to the stage of being able to generate electricity. All of that's directed towards temperature, the depth, the permeability, the size, the productivity, the longevity. You don't want it to just go away. It has to stick around. Yes.
That full production well that has to produce a lot of fluid, that's like a 10 or 12 inch diameter well.
They telescope. usually start off with a 20-inch casing at the surface, a near surface casing of 13 3/8, a production casing just before you get into the reservoir of 9 5/8 inches, and the diameter of the hole in the reservoir is usually about 8.5 to 8 3/4 inches. That's standard size. You can go oversized also. So there are limitations. So once you understand the system enough, you can do oversized wells to produce even larger volumes. So there are wells that produce considerably more than 5 to 7 megawatts each. There is a well in the Imperial Valley that is capable of producing 50 megawatts all by itself.
And the cost of that drilling is,
Somewhere between $5 and $7 million per well, including dry wells.
that's to a depth of a kilometer, 600 meters,
Let's say 2.
2 kilometers.
But even an oversized well, since all the cement and dimensions of casing and so forth dictate a lot of price, you can have wells that are only 200 and 300 meters deep that easily cost $2-3 million. Any other questions? Yes.
I just had a question about like the word longevity on there. Like I think about geothermal energy as being renewable, but when I see longevity, it makes me think not renewable.
Let me see if I can answer your question. Will you hold that question for just a
Yeah.
moment? Let me finish the little speech.
Sounds good.
So that's part of the problem with geothermal in terms of investment, because of the long timeline and the risks involved. So that's one of the things about geothermal risks and challenges: long development cycles, large capital outlays, financing hurdles, and potential resource decline. So yeah, that's something to consider. So let me finish with returning to the original source, Mount Etna, the slide that I had that illustrated heat. Mount Etna is one of the largest volcanoes in Europe. It's almost continuously active. So the not so rhetorical question is, where's the geothermal come? That's the challenge of exploration, because not every volcano has the right permeability and the right conditions to have a geothermal system. And that's the challenge of the future. What if you could create your own permeability and circulate your own fluid and not worry about waiting another million years or so for repeated magmatic intrusions to generate a viable geothermal reservoir for you? That's the challenge of the future. So to answer your question about why is it renewable? Well, in a geothermal system, the fluid that you produce really only amounts to about 7% of the heat, and 93% of the heat remains in the rocks. A lot of thermal modeling has shown that without hydrothermal circulation, a magma body in the crust is viable for about 1 million years. And yet, what we know from geothermal systems in general, or mineral systems in general, is that there's repeated intrusions always that keep generating the system. So something like the Steamboat Hills in Nevada is a geothermal system that powers a lot of Reno, exclusive of all the neon for the casinos. That's been active for almost 3 million years. Long Valley, that I mentioned, has been active in showing eruptive products at the surface, again, back to the geology, for at least 2 million years. So ore forming systems are not just generally a one pulse thing. Something like the Comstock Lode in Virginia City. That was the result of probably the hydrothermal system, the 6th or 7th hydrothermal system that existed in that area. Not just the first, but because those sorts of systems tend to generate permeability in the crust and follow permeability in the crust. So yes, renewable. As long as you're putting fluid back in, it's renewable. Other questions?
So kind of follow up on that, what kind of fluid can you pump into the system? Do you can only use fresh water, or you can, because fresh water itself is also a pretty you can't find fresh water everywhere.
True. So that's why binary technologies are extremely important, because you're putting 100% of the fluid back in the ground. You're not flashing off a fraction and losing fluid. You're putting all of it back in the ground to reuse. So it's also reusable as and also renewable. Now, there are a lot of considerations for the future about what you might do with other alternative fluids, specifically in system where, as I said, you've tried to generate your own permeability. Let's think about using something like supercritical CO2. Why not? I'm trying to get rid of that stuff, right? So if we pump it down and bring it back and use that to generate electricity, if we're losing it, we don't really care, as long as we get some back and we can generate electricity with it. Those are advanced considerations.
So by saying creating your own permeability, are you suggesting like hydraulic fracturing or things related to that?
Yes. Let's see. This isn't working the way I want it to. That's okay. So let's consider some of the more advanced efforts for enhanced geothermal systems. The acronym for my company is EGS. We came up with that in the 1990s, long before the DOE ever funded it and took over the acronym for enhanced geothermal systems. But if you could create your own reservoir space, you could put fluid down and get fluid back. And since you just need to drill deep enough to get to the right temperatures, technically anywhere on the earth, you could generate geothermal energy. So that's part of the effort. It's also part of the challenge. So there are a number of enhanced geothermal projects that have been attempted worldwide, starting in the 1970s in the Valles caldera in New Mexico. But of all those geothermal projects, of all those enhanced geothermal projects, very few have produced a full-scale, like 50 megawatt generation system. There are small enhancements at Desert Peak in Nevada and also at the Geysers in Northern California. There have been improvements in production directly related to injecting fluid and recovering that fluid back. The things that are happening in enhanced geothermal research give us a lot of tools to help us out for developing and sustaining geothermal systems, but not necessarily right now a full-scale geothermal system. It's not that it's not possible, it's just that we have a lot of technical challenges to overcome. So one of the things that the DOE is doing is they finally decided to focus on doing experiments in a manageable system, in a manageable way, to help us develop techniques to do that. It's called FORGE. It stands for Forward Observatory for Research in Geothermal Energy, I think. I'm not good with acronyms, so I apologize. But FORGE actually picked a site in Utah, and they're at the stage where they're actually going to wind up doing different methods other than the ones that that's a dozen or so that have been tried elsewhere, to try and generate a circulation system in the subsurface. And they're at that stage where they're going to complete a production well to go along with an injection well and see if they can do that. But the most important thing to come out of it probably are techniques. And that's also an important investment for research. Other questions? Well, thanks. I appreciate your time.
A few questions from audience.
Oh, okay.
So this Jurassic would you like to unmute yourself and ask your question? Okay, you can. So,
Okay. Well, can you hear me?
Hello?
Let me get to the slide that illustrates.
Hello?
Are you there? Well, if you can hear me, solar prices have come down for solar cells have come down to very, very low. So that's one of the competing things. The other thing is tax credits and production credits. Geothermal has stayed a little bit higher primarily because of increased drilling costs. And that's something that's always being addressed in geothermal systems. What did the MT resistivity survey show of Newberry Caldera? High resistivity down to about 300 meters, intermediate resistivity from about 300 meters to say 500, and then moderate resistivity below 500 meters. What's the status of EGS in the US right now? I just went over the Forge system, and they're at a stage where they're about to drill a production well to test circulation within the system. No. Okay. Right.
No more questions. So here, so next week, the same time, we'll have Adam Bursey from UCSD. It's about unplanned results. So see you next week.
So that will be another person.
No, well, we haven't decided that yet.
Okay.
Yes. So we have a few spots. If students want to have lunch with Jean, you can come here and we can go together.
Yeah, I didn't email you back, but I'm gonna come for lunch.
Okay.
Yeah.
Thank you.